Okay, so welcome back to another talk at AATRN. Today we have Beatriz Pascual Escudero, who will be speaking to us about using algebraic geometry to detect robustness in reaction networks.
Thank you. Thank you everybody for joining, and thanks to the organizer for the invitation. It's very nice to be allowed to give a talk in your network. And yes, I'm going to be explaining to you how one can use algebraic geometry in the study of reaction networks, and in particular I will be interested in robustness. I will first try to give you an idea of what we do when we study reaction networks, and then I will go into my problem of robustness. Let's see how far we get. But before so there will be reactions, and there will be cells, and there will be a lot of things. So before I lose the focus, let me tell you what kind of math I'll be doing so that everybody knows what to expect. So this part is fairly simple, so just to help you focus. I will be considering dynamical systems. And those dynamical systems will be modeled by ODEs systems, autonomous ODEs of this form. So the right-hand side are polynomials. So I'm modeling the evolution of each of the variables x1 to xn by a polynomial formula. Okay, this is a kind of dynamical systems that I'm considering. And then I will be interested in looking at the equilibria of this system. So this means I will check when the xi over dt is 0 for all the variables xi. And this means just looking at the solutions to a finite set of polynomial equations like the one I have here. And for me, this is just an algebraic variety. It's a set of solutions of a finite set of polynomial equations. I can think of them as, well, I can think of them in many different fields. For reasons that will appear later, I will be interested in only looking at the solutions which are real and positive. And I have some pictures on the right. Yeah, you can see the whole algebraic varieties. It's the kind of things that we algebraic geometers like. And in this case, I will be interested in the part of these varieties which is in the positive order. That's all. And once that I have one of these objects, I will choose a special variable xi. And for this xi, what I will be looking is at whether this variable preserves its value when I look at all the positive solutions to this system. So I will look at the whole set of solutions and think, well, does this value, does this variable always take the same value, independently of which point I look at? This is what I will mean by robustness, roughly. So this is what I will be doing. I will be considering a dynamical system, looking at the positive equilibria, and then thinking whether they are contained in some specific hypersurface of Rn. And now the reactions come. So let me give you an example to try to show you how we build such a dynamical system from a network. So our reaction network is a set of reactions. There are some species involved. In this case, my species are x1 and x2. These species can be chemical species in a tube, or they can be proteins in a cell, or they can be some organisms in some environment. So they are interacting species, and their interactions can be represented by a graph like this. So each of these arrows represents a reaction, the first reaction. So I will be thinking of proteins or molecules. So let me talk about molecules. One molecule of x1 meets one molecule of x2, and then eventually with a certain rate that depends on a certain constant, which would be what I will call a reaction rate, it eventually becomes two molecules of x1, of x2. And the second one just means one molecule of x2 will eventually become one molecule of x1. This is what this encodes. And once that I have such a network, I can construct a dynamical system to look at the evolution of the concentrations of these species in time. And this, as I told you, will be given by polynomials. And how do I construct these polynomials? Well, these polynomials are very particular because they're only built up by monomials, which depend on those here. Those here are the reactants. So they're the sources of the reactions. We have the source complex and the product complex, which is what they become afterwards. So each reaction will give us a monomial, well, a term, but let's start with the monomial. And it will give us the monomial in the following way. The first reaction, so the monomial will be, for the first reaction, the monomial will be just x1 times x2. And this comes from looking at the variables. The variables encode the concentrations of the species. I don't know if I said that. So we will take the variables that are involved in this reaction, and we will set the exponents coming from the coefficients here. So the coefficients here are 1, so I just have x1 times x2. And for the second reaction, I have just x2. If I had down there 2x2 instead of x2, then I would have the monomial x2 squared. It's simple as that. So this, I didn't say that, even if it's written. This is assuming a certain kind of kinetics, which is mass action kinetics, which is kind of common, and is the one that I like because it gives me polynomials in the first place. I can be a little bit more general. I could allow something that it's not polynomials, but generalized polynomials with rational exponents, and I could kind of do the same analysis. But for simplicity, let me assume this kinetics. And with this kinetics, I build the system in this way. So I have my two monomials, and if you look at my system, yeah, the polynomials are only built up by monomials coming from there. And to each of these monomials, I multiply. So the first one is for the first reaction, so I multiply by the rate constant attached to the first reaction, and the second one, I multiply by the rate constant attached to the second reaction. So this gives me a vector of monomials, and then I will multiply this vector. So my polynomials are linear combinations of these terms, and I will build them by multiplying by a matrix. And this matrix encodes the information of how many molecules of each species are created or consumed in each of the reactions. So this matrix N has one row per species and one column per reaction. And the entry Nij will have the number of molecules of Xi, which are produced in the reaction J, in the J's reaction. So let me build a matrix in this case. First species, first reaction. Well, I start with 1 x1, and then in the product I have no x1, so I lose 1. And in this same reaction, so the same column of x2, I also lose 1. No, sorry, I win 1 x2, right? I start with 1 and I get 2, so I win 1. And for the second reaction, it's the other way around. I lose 1 x2 and I gain 1 x1. So this is my matrix N. And if I multiply by my vector of monomials, I get exactly the system that I have above. So this is how the information of the reaction is encoded in the system under the assumption of mass action. Right. So I get these two polynomials. And now I want to study the common solutions to the equations f1 equals 0, f2 equals 0. First thing that I can do, I can realize that the second equation is just minus the first one. So I have two polynomials which are actually a multiple of each other. And I can stick to one of them. So let me stick to the first one, maybe. I can also factor out x2. And then I have this equivalent polynomial. So what are the positive solutions here? Well, for this to be 0, either x2 is 0 which doesn't give me positive solutions, or the second factor is 0. So if I look at the positive steady states, and I will write the positive steady state variety by this orange D, those will be the points which satisfy these conditions, and that are pictured on the right. Okay, and I told you that the second equation is just minus the first one. Well, this means that if I add the two equations, I get 0. And this is the same as adding the x1 over dt plus the x2 over dt. So this means that this quantity x1 plus x2 is constant in time, right? It's preserved. So what can I do with this? With this, I build the so-called stoichiometric classes. And this constant will depend on the initial condition of my system. So say that I start with a certain quantity of x1, this quantity of x1, and this quantity of x2, just to make my life easier. So I start with a certain pair of concentrations, x1, x2, which is placed there. Then when the system evolves, the concentrations will change, but well, there will be a line corresponding to this equation, right? That contains all the possible states that I reach in the system. So when I reach an equilibrium, this equilibrium needs to be in the orange line, but it also needs to be here. So starting with this initial condition, I will reach this equilibrium. If I change to another stoichiometry class, then I will just move to a parallel line. So those stoichiometry classes give me linear, some other linear algebraic varieties that I can intersect with my steady state variety, and that depend on the initial concentration. So going back to, this was my example, and let me go back to the general setting to tell you what things can I study on reaction networks. I have my ODE system, which is given by polynomials. Like this, for the things that I will be telling you, the system can come from somewhere else. It doesn't need to come from reaction networks. This is just the example that I'm using as the motivation. But as long as they're polynomials, I'm good. I will be looking at the positive equilibria, so the positive solutions of all these equations. But as I told you in the former example, I sometimes can remove some of the equations just because they are linearly dependent. So I can also be looking at a subset of these equations. I will just rename them by G, and maybe S is less than N. In that case, I will be cutting out with some linear spaces. And just a technical condition that I will need for my results, those solutions will be called non-degenerate if the Jacobian of the function g does not vanish, has maximal rank, now it's not squared necessarily, has maximal rank of x. So this is just d of g1 or x1, right, this matrix. And S times n matrix. That I will be evaluating at C. If the rank is maximal, then the steady state is non-degenerate. Otherwise, it's degenerate. And as I showed you, one example of building this kind of systems comes from reaction networks. Here I'm telling you, well, x to the b encodes this vector of monomials. B would be the matrix which has one column per reaction, and this column has the exponents of all the variables in the corresponding monomial. So it's an S times R reaction. And this gives me, with mass action, it gives me a polynomial system. So if I have fixed reaction rates, then I get a fair system of polynomials, and I can try to understand this object here, that as an algebraic geometry I would like, which is a subset of an algebraic variety. And I can ask questions about this set of solutions. But sometimes studying this set is not so easy. And moreover, in some cases, these reaction rates are not fixed values. So those reaction rates, maybe I don't know them. Maybe I have a model for my network, but I don't really know the rates at which the reactions occur. They are sometimes measured in laboratories. They can have errors. So it's sometimes interesting to be able to understand the behavior of the network in a way that it does not depend on the constants, so that I can study the whole family. So how the behavior is for all the possible values of the parameters k, and maybe say something maybe about all the parameters. So typical questions in reaction networks are, for instance, I showed you this stoichiometry classes. It cuts my variety only in one steady state. So is there any parameter for which it cuts the variety in several steady states? So can I have several distinct equilibria starting from the same initial condition? So does this happen for all the parameters, or is there a region in the parameter space for which it happens? This kind of questions. So sometimes I'm interested in studying the whole parametric family of polynomial equations, and also this means the whole parametric family of steady state varieties. And now I have a system with the variables in the species, and then the coefficient have maybe many parameters, so it becomes computationally very complicated. So now I come to my problem. My problem is studying robustness. And I will study it in two versions. One of them is, well, I start with steady state, and then something happens in the environment. Maybe it's perturbed by something. Maybe I add some amount of a very small amount of one of the species, and then the system is no longer at equilibrium. It will evolve until it reaches a new equilibrium, and maybe I want to compare the former equilibrium and the new equilibrium. And I want to see, well, I was choosing a special variable. I want to see, in particular, whether this variable changes its value when changing to the new equilibrium. Another option, a more strict option is, well, no matter which point I look at, this variable always has the same value when I'm at equilibrium, which is the first one that I mentioned. So let me go over these two, but first let me try to give very fast an example to motivate. So let me go to the biology, and also so we get our mind out of the formulas for a little bit. So there is this mechanism, this bypass here that I don't dare trying to pronounce, which is a mechanism that takes place in some plant cells, in some fungi cells, in some unicellular organisms, some bacteria, that transforms fatty acids into glucose to build the structure of the cell. So this allows the growth of the cell, and it uses carbon. And also the Krebs cycle uses carbon. And for some bacteria which live well, first let me talk to you about the paper, the role of this thing. This I here is an enzyme. It's the IDH enzyme, isocitrate dehydrogenase or something like this. I would say IDH. This is my green enzyme, which decides where the carbon goes to one or the other mechanism. So this one here gives energy to the cell. This one allows the growth of the cell. And there are some bacteria which live in some environments where the carbon needs to be really precisely divided into these two mechanisms. So it's very important that this enzyme divides the traffic in a very precise way. And while it's green, it's active. So it's doing that job. But when this enzyme gets a phosphate group, it can become inactive, and it no longer works for that. So I'm not so interested in the mechanisms, but I'm interested in the process by which the enzyme becomes inactive and active again. And for these, there is this other enzyme, which is the assistant, that helps IDH become active or inactive. So when this assistant enzyme meets an inactive I enzyme, some reactions may occur, and then eventually I get an active enzyme. And on the other hand, with different rates, I omitted the rates here, but by means of these intermediate species that was created here, an active enzyme becomes inactive. So this K helps my enzyme get or lose this phosphate group, and this is our reaction network. And here I was telling you that for some bacteria, it's very interesting that, it's very important that the regulation is made precisely. So if there is some change in the environment and some of the enzymes is lost or some is added, it's very important that when the system reaches a new equilibrium, there is the right amount of this green enzyme. So no matter if I add some other amount of the other enzymes, when I reach an equilibrium, I want the system to be robust to recover its original state in the sense of the value of the concentration of this enzyme. So I will rewrite this reaction network. I just changed the names to the original notation, but I kept the color. So the active enzyme is X4, the green one, the inactive one is the red one, and the assistant one is the blue one. I can, again, build my system, which will have 5 polynomials. I just wrote the first one, so you can see the monomials there. And in this case, I can, with some work, I can try to study the set of solutions. And the set of solutions can be parameterized by 2 parameters. So this is a surface in R5. And you can see the first 2 concentrations are the parameters, the second one depends on them. And actually, the third one depends on them, and the fourth one does not depend on any of them. So if you look at this quantity, it does not depend in any of the parameters. So it's constant. It only depends on the case. So for any point in this set that I find, the value of the green enzyme, the concentration of the green enzyme is constant. So it's very robust in that sense that I was looking for. So this is the motivation, the biological motivation. And now I will define what Skinner and Feinberg call absolute concentration robustness, which is precisely this. No matter which steady state I look at, Xi has a fixed value. So this is the strongest definition of robustness. So my goal here is to try to detect this. This is interesting for certain processes, as I showed you an example, but it's not so easy to find. If I can study the steady state variety, then yeah, maybe I can decide as I did with my example, but sometimes I cannot do all these analyses. Maybe it cannot be parameterized as easily, or I want to study the whole family. And then there is not, there was not a standard way to check that for any family of systems. And what we did in our joint work with Elisenda was try to find a criteria that allows me to say something about this. And we found a necessary criteria that I will try to reach. So first, let me think of what this is. Geometrically, ACR, I mentioned this earlier, means that, well, I'm choosing my special variable, xi, and I'm saying, well, I need all the set of solutions to be contained in a hyperplane, which is a translate of a coordinate hyperplane, right? So this just stands for the set of points where xi minus c equals 0, right? This is the notation for algebraic varieties. So I mean here all the points where this is 0. And I'm looking at the real points. And in fact, I'm only interested in the positive points. I don't care what happens in the negative ones. But this is the condition. I need it to be contained in a hyperplane. And just because I will be writing this afterwards, this is a notation that I use for an ideal. So the ideal generated by F, this means all the combinations, linear and nonlinear combinations of the polynomial, which appear in the right-hand side in my system, which they are all useful because any solution to an equation of the form, any common solution to all these equations is also a solution to any combination of equations that I can build from there, right? So there is one thing that I can do. If I can find that this equation is actually a combination of my original equations, then I have an algebraic condition there. This set I said is an algebraic variety. Sorry, I skipped this. So if I consider all the combinations of my original polynomials, I can as well consider all the combinations of the reduced set of polynomials, because here I only had some which were linearly dependent, and I just removed them to get those. So it's the same set. And I told you this is a subset of a real algebraic variety. So the positive solutions is a subset of the real solutions, which is a subset of the complex solutions. And when people do algebraic geometry, we sometimes try to go from the varieties to the ideals to see if we can say something based on the polynomials that are contained in the ideals. And this is one of the cases. So if the polynomial xi minus c turns out to be a combination of my original polynomials, I know that all the solutions to the original polynomials are a solution to this polynomial, so I have ACR. This condition is satisfied for all the points in my set. But unfortunately, the converse is not true. So if I cannot find this polynomial in my ideal, I cannot say that there's no ACR. So I need to dig in a little bit more. Let me show you a couple of examples very fast.
Can I ask you a quick question, actually?
Yeah, sure.
So if I understand the statement that the converse isn't true, it means that it may happen to be that it sits inside the hyperplane, but it can't be produced via polynomial algebra. Why would it?
Yeah, exactly. Well, if it can happen that all the complex solutions, it can happen that all the real positive solutions are in the hyperplane, but there are some negative solutions which are not in the hyperplane. And then the ideal here does not care about positive or negative. So if there are some solutions which are not in the hyperplane, even if they're negative, this equation will not be here, because if it's here, then it will be satisfied by all the solutions, and it's not the case. It can also happen that it's satisfied by all the real ones, but not by all the complex ones. And that can also be a problem. And it can even happen that even some weirder things can happen, but maybe the next couple of examples will give you some ideas about this.
Thank you.
Afterwards, you will let me know if I answered your question. So yeah, I'm considering all the combinations of my original polynomials or of the reduced polynomials. And if I find that the polynomial is there, I'm very lucky because I know that all the solutions are contained in this hyperplane. But otherwise, what can happen? Well, let me look at the first example that I showed you. These two polynomials that I told you, the second one is just minus the first one. And I also told you I can factor out x2. So my ideal is just generated by this, and the positive solutions are those here. So there is not such a polynomial in my ideal, but there is a product of this factor by some other factor which does not bring any positive solutions. This is one thing that can happen, right? So not all solutions satisfy this, but all positive solutions do. And in this case, my system has ACR for x1. Here is a little bit more complicated example. This one does not come from reaction networks. So again, I have 3 polynomials, but one of them is just a linear combination of the other 2. So if I just do a little bit of manipulation with them, I realize that my ideal can be generated by these 2. So this would be my G1, and this would be my G2. And if I try to look at the positive solutions here, some things happen. Not all not all complex solutions are contained here, but all real solutions are, right? So from here, I could say, yeah, solutions need to satisfy either this or this, but if they don't satisfy this, it turns out by using the other polynomial, they're not real. So these kind of things can happen. This example is a little bit tricky because all the points here are degenerate, which is a thing that I said in the beginning was, yeah, I needed a condition on that. But yeah, this kind of things can happen. So this is the situation for ACR. And now let me turn to the local notion of robustness. So this is used in metabolic analysis to determine the degree of robustness. And what I'm doing here is I look at one positive steady state, which now needs to be non-degenerate and also non-degenerate with respect to the stoichiometric class. I will say now what it means a little bit. But geometrically, what it means is I choose a steady state. So say I choose this steady state, and then I move a little bit. When I move a little bit, I change the concentration a little bit, some of them, and then eventually the system will reach another equilibrium. And if I only changed it a little bit, this movement will take place like inside of the steady state variety. So I will be moving inside of the orange curve a little bit in some of the directions. If I am in a curve, it's very restricted, but imagine you're in a hypersurface, like in a surface in 2D, and you look at a point, and if it's a manifold, here is where the non-degeneracy comes. If it's a manifold, you can consider the tangent space, and you can move a little bit in some of the directions of the tangent space, and then you will, after the system returns to an equilibrium, you will fall somewhere in the manifold close to where your point was, and you can compare these 2 points in the manifold. So yeah, what I do when I perturb is I'm moving in some of the directions of the tangent space. And this condition here with respect to S, it means not only it needs to be a manifold in that point, so the Jacobian needs to be of maximal rank, but also the tangent space need to cut nicely the stoichiometric classes. So if the stoichiometric classes were at the same direction as the tangent space, this would not work so well. So I'm imposing that they cut nicely. So for instance, here, if I fix this steady state and I had my stoichiometry classes as before, when I move a little bit, I will change into another stoichiometry class. So maybe I add a little bit of x1, then I will go to another stoichiometry class, and afterwards, the system will return to equilibrium. It will come here. And I can compare my original steady state and the new steady state. Well, in this case, they both have the same value in x1, right? And this is because, well, in this case, it's because it has ACR, but it is, to be a little bit more precise, this is because the tangent space to the steady state variety at that point, at my original point, is perpendicular to the xi axis. So wherever I'm moving perpendicularly to the xi axis, which does not happen in the first picture. Okay, this is the idea behind the sensitivities. So zero sensitivity, at a steady state in a certain variable means that all the tangent vectors at the steady state variety at this point, well, if you look at the tangent vector, the ith entry will be 0. This is what it means. Is that understandable? I see you unmuted yourself.
Yes, I actually wanted to ask a question from the chat.
Okay.
So we have a question from Daniel Scott. It's about the previous slide. So if you could jump back, I'll ask the question and maybe Daniel can clarify if there's any need. So he says, regarding the previous slide, it seems like one could produce a lower bound than the number of cases you'll miss using the combinatorics of your examples. Is this possible or no?
What do you mean by the number of cases you'll miss? By trying to just find this equation?
Sorry, yeah, I can clarify. I wasn't sure what the protocol for questions in this seminar is. Yeah, I just meant, you know, you have your criteria for ACR, and you're discussing ways, you know, that the sufficiency condition is not a necessity condition.
Mm-hmm.
And I was wondering if you could bound the relationship between, you know, the number of cases that you'll pick up from the sufficiency versus, you know, the number of cases that you'll miss. Does that clarify?
How would you measure number of cases? Like which kind of?
Yeah, I mean, it's a, you know, it would
what
be.
What can go wrong?
Yeah, question about, you know, I guess you would need some measure on polynomial spaces or something, but.
I guess so. I think I can define them, but I don't know how to quantify them in any way.
Okay, yeah, thank you.
Thank you for the question. Okay, so coming back to the zero sensitivity, yeah, I was saying that the sensitivity at a certain point being 0 means that no matter which perturbation I perform, when I reach a new steady state, the value of xi is again the same. So a perturbation, I mean a movement, like a small movement. So I would show more examples so that this becomes clear. But it makes sense to think that if I ask for ACR in xi, so if I ask that the value of xi is the same at all points, it definitely needs to be the same in the neighborhood, right? So if I change a little bit, I need xi to remain the same if I'm expecting that it's the same everywhere. So it's a necessary condition. Zero sensitivity is a necessary condition for ACR. This is why I meant, why I was saying this is a local versus global. And it turns out that checking zero sensitivity is very easy because you just need to look at the Jacobian matrix again. And well, I told you that the non-degenerate point would make this the rank of this matrix be maximum. Well, if I remove the column corresponding to xi, so the ith column, and then this makes the rank drop, this means that there is zero sensitivity, because what I'm checking with that is precisely that the tangent line to any curve through that point is perpendicular to the xi axis. This is exactly the check that I'm doing by looking at the drop of rank of the Jacobian matrix when I remove the column corresponding to this species. This is not, I mean, it's not very deep, but one needs to think about it. I don't expect you to see it, obviously, but it's not very, the ideas here are not very deep. You just need to do the computation. So this is what zero sensitivity is, and it's a necessary condition for ACR. But it's not a sufficient condition again. Why it's not a sufficient condition? Well, let me look at this network. I can, again, build a system for this network. And if I build a system and then reduce to only linearly independent equations, I realize that there is only one equation defining my steady state variety, this equation here. And it has 4 factors. So the first 2 don't add any positive solutions, right? Because for those two to vanish, I would need one of the variables to be 0. And I only need to focus at the third and the fourth. And the fact whether they give me positive solutions or not, it depends on the discriminant. In this case, let me look at one specific choice of variable values for the case. So if I fix this set of variables for the case, this set of variables for the case, this is how the steady state variety looks like. So it's 2 lines. It can happen depending on the value of the discriminant, the two lines become just 1, or that one of them becomes negative, or the 2 becomes negative, maybe. But for this particular choice, I have 2 lines. So here it is true that I have 0 sensitivity, because if I stay at any steady state and I move a little bit in the neighborhood, I will fall into another steady state which has the same value for x1. But it's not the same value everywhere, right? I have 2 different values. I have this value and this value. The only thing is, to go from one to the other, I need to jump from one line to the other. And this will not happen by moving slowly, slightly. So this is what can go wrong when trying to join ACR with 0 sensitivity. I can have several lines, I can have several components, so my steady state variety can be made by several components. So this brings me to the definition of local ACR, which is something in between. It's not as local as 0 sensitivity, but it means the same thing as ACR in each of the irreducible components. So if I have an algebraic variety, I told you the set of solutions of a finite collection of polynomial equations, I can always write it, decompose it into the smallest possible algebraic varieties, right? So I can find minimal decomposition, at least theoretically, into pieces which are themselves algebraic varieties. So in the former case, I had 4 lines, actually. 2 of them were the axis, and the other 2, let me go back to the picture. So here, this gives me one component, this gives me another component, and then the other 2 factors give me the other 2 components. I have 4 components. All of them are algebraic varieties. Only the first 2 don't intersect the positive orthant. So I can write my whole algebraic variety as the union of 4 algebraic varieties. And when I intersect them with the positive orthant, I only need to look at these 2. Well, if each of them has a fixed value for x1, then I have local ACR. And well, theoretically, one could check when one builds the minimal decomposition, one could find the ideals associated to all these pieces, and one could check if the equation is contained there, and then we will come to the original problem of, well, sometimes I'm also missing cases there. But this only happens sometimes, in fact. So this is what local ACR means. It means in each of the irreducible components, I have ACR. I have a fixed value for each component. And the number of components is always finite. So it means I actually have a finite number of values that the variable xi can achieve at positive steady state, which is also interesting. I have some kind of discrete range of states for the species xi at steady state. Yeah, this is just what I said. So I have a constant for each variable. And of course, ACR implies local ACR. It needs local ACR, but yeah, if I have several components, the converse is not necessarily true. But it's true sometimes. It's true when, well, when I only have one component, when it's irreducible. And it could sound like a very strong statement, like a very strong assumption, but it is the case in many networks that are of interest. So there are several classes of networks studied, like toric networks, for instance, which are parameterizable and they are irreducible. And then this is the same thing. ACR and local ACR are the same thing there. And it's also the case if it's connected, right? If all components touch, or they touch each other 2 by 2, yeah, the value for the ACR variable needs to be the same at all of them. So sometimes it helps. So this is the picture right now. I have ACR, which means one line. Well, I'm picturing lines here, but actually it doesn't need to be a line. You can go to 3 dimension and maybe you have a curve which is contained in a hyperplane. Yeah, like the circle that I draw in one of the examples. Local ACR would mean having something like that. 2 lines or maybe 2 curves containing different hyperplanes. Not necessarily straight, but curves, but they are in different hyperplanes, parallel hyperplanes. And then local ACR implies 0 sensitivity, as I told you. And this one is the one that I already know how to check, and it's very easy. So how can I come back? Well, this one, I told you, well, I cannot do anything about it. If the variety is irreducible or connected or satisfy certain things, it will be the same. Otherwise, it will not be the same. So I will focus on that one. And it turns out that with a little bit of work in algebraic geometry, one can conclude that under very nice hypothesis, they are actually the same. And this is where our result comes. I consider my system of polynomials, and I reduce it. I get only the linearly independent ones, G1 to Gs. And I look at this stoichiometric class, this stoichiometric space, the linear space that defines the classes where the different initial conditions lead me. And I can consider all the irreducible components. So once I intersect my algebraic variety with the positive orthant, so I only look at the positive solutions, I can take the original variety and check which of those irreducible components, which of the irreducible components of my algebraic variety do intersect the positive orthant, and I only choose those. Those are the ones here. Well, the hypothesis that I need is the same, is the following. I need that for each of those irreducible components, there is one point there which is non-degenerate with respect to S. So there is one point there where the Jacobian has maximal rank and the tangent space cuts the stoichiometric space nicely. This is what I need. If I have one point in each component which is non-degenerate, so degenerate points come when I have singular points or I have something which is of a higher dimension than what I expect. This is when they come. So normally I can expect that most of the components have such a point. And if I can guarantee that I have a point in all the components that intersect the positive orthant, then the following are the same. It is the same having local ACR with respect to xi as having 0 sensitivity in the points, in all the points where it makes sense to look, so not the singular points. And it is the same as checking that the rank of the Jacobian matrix, which was full, drops when I remove the if column. So what I'm proving here is that actually this criterion that I told you was easy to get from the sensitivity is also the criterion for local ACR under this hypothesis above. Yeah, and this way you relate all of them. So you can check local ACR, which is necessary for ACR, and in sometimes the same, and in some cases the same, by looking at this drop-off rank matrix. And you can tell me, well, but here you are computing this Jacobian matrix, and you need to evaluate at all the non-degenerate points in your steady-state variety. So you need to know all the points of your steady-state variety. Well, depending on what information you have, that could be true. But this theoretical result leads us to a very nice criterion that one can use to study the whole family for the parametric system. So this is the picture, the complete picture. Yeah, ACR implies local ACR, which implies zero sensitivity, which I can check with linear algebra. And under the non-degenerate point hypothesis in each irreducible component, I can also check local ACR using this criterion. And with this, well, sometimes I have something to do, sometimes not. So what happens if I consider the whole network and I don't know the parameters? I consider the whole system, parametric system, given like this. And I do the same. I reduce, I remove the linear dependencies. I look at the family of algebraic varieties. And I look at the family of irreducible components. I don't need to compute it. I just know that it exists. If for all case such that it makes sense, so it makes sense to use the former criteria, I can use the former criteria. So for all case such that in all the irreducible components, I have a non-degenerate point with respect to S. When I apply my criterion, I get that it is equivalent to have local ACR with respect to Xi, or to have zero sensitivity in all the points which are in which the variety is a manifold. And now I would need to check the rank of the Jacobian, right, to use the criterion. But instead of the Jacobian, I can use an easier computation, which comes like this. Instead of the Jacobian, so checking the drop of rank of the Jacobian when I remove the column I means just look at all the minors which don't include the column I, right? So now I will look at all the minors that don't include the column I, but instead of the Jacobian matrix, I will look at this matrix. And this matrix is just taking my N matrix from the beginning, removing all the rows that I should remove so that I get only the corresponding S, because removing linearly dependent equations means just removing linearly dependent rows on N. Then multiply by a diagonal matrix where you put a vector in the kernel of N, and then multiply by the transpose of the matrix B that I told you had as columns the exponents of the monomials that were coming from the reactions. So this matrix is just a matrix of integers, and here I just need to find generators of the kernel, which is way easier than finding all the points in my steady state variety, right? And just to finish, let me show this in an example so it's a little bit more clear. Let me go to my IDH enzyme example. I can write down the matrices, which are this big. This is the N matrix after removing two rows which were linearly dependent. This is my V matrix. I find a generating set of the kernel. So there are three vectors that generate the kernel. So any vector in the kernel of N is of this form. I can write with three parameters. Then I compute this product, and this is what I get. If I remove the column corresponding to the green enzyme, right, which is the one in which I was interested in ACR, well, these two columns are the same, and it turns out that these three are actually linearly dependent on each other. So once I remove this column, the rank drops to 2. And this is how I use my criterion. You can see that it's way more simple computationally. And yeah, I have ACR in X4, and this is all that I wanted to tell. So thanks for listening.
So thank you so much, Beatriz. Please unmute yourself now and applaud the speaker. Okay,
yes,
so now
sorry for going a little bit over time, I think.
Oh, no worries. Are there any questions for our speaker? Yes, Daniel, feel free to unmute yourself.
Cool, thank you. This was great. Thanks for the great talk. This might be a little bit skew to what you were doing. So if you don't have a great, if it's not super on topic, that's fine. Just whatever. I'm wondering how you could generalize this to a situation where you don't have conservation of mass. So in a lot of the applications I would be interested in, you basically would have some dispersive concentrations. Like these concentrations wouldn't follow the stoichiometry that that conserves them as you've written it. And so I'm wondering what you would need to do to move in that direction.
Thanks for the question. So there is one thing. If let's see if I understood correctly. So you would have some system like this, but you need all the equations. You don't have any linear dependencies, right? That's what happens. Well, the thing is that the criterion that I'm giving for local ACR, well, local ACR tells you that you have finite number of values. So each component has a number of values. If you have this kind of system and there are no, well, if there are no dependencies at all, if you have only finitely many solutions, then local ACR is trivial, right? So if you have 0-dimensional solutions, then local ACR is trivial because, yeah, of course, in each point you have one value because you only have one point there. Otherwise, so you could have nonlinear dependencies, right? I think you will have some degeneracy there, probably. Otherwise, okay. Maybe if you can give me an example. Yeah, I didn't move in that direction because in this kind of systems, the problem is that if you don't have any conservations like this, then you have finitely many points, and then ACR is trivial. So there's nothing you can say about. Yeah, you cannot say anything about ACR either.
Yeah, I mean, I guess I was imagining that you would have some some mixture of things that you're conserving and things that you want. But yeah, it sounds like it was a bit out of scope. So thank you very much.
Thank you.
Any other questions? I actually have a very quick question. Could you go to the slide again where there's kind of the plot that looks kind of, I guess, cubic? Maybe. I hope that's descriptive.
This one?
Yeah, so it does seem like in a certain, like the x1 isn't constant, but it does, let's say, stay in a narrow band. And it depends on what you consider to be narrow, but is there a way of using, is there an algebraic geometry approach to say that if it isn't constant, that there is some inequality? Let's say it doesn't deviate more than some fixed epsilon from C.
I never thought about that. Now that you say it, maybe it actually makes a lot of sense for the applications, right? Because maybe it's not constant, but it stays close. And yeah, not that I know of with algebraic geometry, but might make sense to take a look at it. Thank you for the question.
Sure, that's interesting. Okay, if there are no other questions, so thanks again to Beatriz.
Thank you.